The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Evolution of rebar, really just looking at the past, present, and future, where we've been and where we're going. So start with glance in the mirror. Now, common mistake, grade 60 rebar was not actually an engineered material. It started out, it was kind of showed up in the 50s and eventually in 1966, the various versions of, and at the time, you know, just kind of look at what you had. You had AstroTurf had just come out, first using the Astrodome, hence the name. Bonanza was the big show. Star Trek First Air, that's far more important than Bonanza. Miranda against Arizona, which ultimately coined the term Miranda rights. Stamp was 5 cents, gas was 32 cents. 3 different phone systems just to make it easy. And then A706, really the first step forward towards a truly engineered rebar grade as opposed to just what happened to be. And you look back then, Dynamite, Dick Nixon, Super Bowl ad only cost $103,000. Of a number 5 rebar, it's basically a 5/8 inch round, not restricted in just about anything. They didn't put, the only limit they put was on a really, really high phosphorus, and the reason they didn't was because steel back then was mostly ingot cast. Now, that in and of itself doesn't matter, except that rebar was the worst part of the ingot. You took the part that had all the crud, for lack of a better way to put it, just floats to the top. You get this tapered shrinkage cavity, and then you cut that off, and all the good stuff went into something else, and that leftover shrinkage cavity went into rebar. Then you had all your missed chemistries. Well, we were trying to make 4140, we missed it. Well, no problem. It's right or it's rebar. That's the material that we're basing all of this research on as our basic, this is our gold standard. And it was all the garbage and trash that sort of just, of course, I think everybody recognizes these standards, A615, A706. We've got, 3 through 18 bar on A706. We got the 55 max carbon. We've added grade 100 to A615. No real surprises there, right? So, but we are going to take a look at some of the manufacturing improvements that have happened along the way since the 1960s. 1, continuous casting. And if there's anybody to thank for this, it's probably Nucor. So this was a remarkable step forward. Instead of having that ingot cast step and then taking the ingots and rolling them into billets and then taking the billets and rolling them into bar, you skipped a whole step in there. Now, what that also did was it reduced your average reduction ratios from the ingot to the final bar. So steelmakers were forced to compensate by reducing our carbons, increasing manganese, and starting to use microalloys instead of just using a 45 carbon for everything. Now, what this resulted in, all of these things, we have improved bend test reliability compared to then. And generally, our steel is cleaner now than it was in regard to non-metallic inclusions. Again, because we have really, in the industry, we're no longer looking at steel as, or rebar as whatever we couldn't do anything else with. It's truly, on our end, become an engineered product from our mills. We've also improved our ability to measure things. So you look at the spectrometers, the capability of the spectrometers versus a guy with a grinder that was calibrated at 4,400 RPMs, and based on the way the sparks came off the grinder, that was how you told the chemistry of the steel. I wish I was making that up. Then you have the tensile testing capability. You used to have this big giant dial, I wish I had a picture of it, and it would come up and it would stop and then it would keep going, and that was how you got your yield strength and your tensile strength. You had none of the instrumentation that you have today. So taking one last look at things, fundamentals of iron still apply. It doesn't matter how good we get as steel makers, you can't cheat physics. Strength, as far as a material is concerned, is the ability to resist changing shape or breaking when subjected to force. So things like substitution, interstitial hardening, carbide formations, grain refinement, quenching the steel, these things shift towards the right, towards strength. And in return, we're giving up something on the ductility side, because the definition of ductility is the ability to adapt to force by changing shape. They're direct opposites. So things like annealing, tempering, spheroidizing, these are examples that will take the steel towards the ductility, but sacrificing strength to do so. So in the end, almost every single grade of steel out there is actually a compromise between the strength we think we need and the ductility we wish we had. Now, steel in reality is the ultimate Rubik's Cube. I got one here. On an atomic level, this is what the iron atoms do. They arrange themselves in cubes. And what happens, as long as the cubes are in a nice, neat square, everything moves, right? It adapts. You subject it to force, it moves, it changes. Now, you get something a little bit off kilter, and you go to change it. It's a little harder to move, right? You get it far enough off kilter, you hear it breaking, right? So that's the problem with overstrength. It did break, it just didn't shatter. But that's the problem with overstrength. You go far enough on that molecular lattice, you get it far enough out of kilter, and it's just not going to adapt anymore. It's just going to break. Okay? The other thing is, it's a giant puzzle because you can't just change the blue face without changing the whole rest of the cube. You know, I want to keep everything the same, and I'm just going to change the ductility a little bit. Doesn't happen. You change the whole steel when you change any one thing. And that's been one of the great challenges with moving towards higher strength is how do we change the things we want and make the fewest sacrifices possible along the way. So a few examples of how strengthening occurs. This is going to be a science lesson, so for those of you who slept through science class, you got a perfect nap coming. So what carbon does is it takes the steel away from a cubic arrangement and it turns it into something called cementite that really, for lack of a better way to put it, looks like a big giant molecular snot ball. If you look at this micro etch on the right, all the white areas are ferrite, which means they're cubic arrangement. It means that those white areas of the steel can adapt to force. When you look over here and you see where there's a much higher carbon addition, the carbon additions are that black area, and it looks like this. So in this steel, only the white areas can adapt to force. The black areas cannot adapt to force. This is why when we add carbon, we lose ductility in the steel. There's just fewer regions of the steel that can actually adapt. Then you have grain refiners. Now what grain refiners do, steel grows in grains. Every one of these little circles and things where you can see a boundary around them, those are called grains. Now what happens in a grain, if you look, there's one grain, there's a grain, but the atoms are arranged in a different direction. Here they're arranged in a third different direction. It's geometry. So you get reinforcement, you get improved strength through geometry. Then you have this region of misfit where everything's out of line. That also contributes to strength. So what happens when you add more microalloys, your grain size shrinks. You go from this to this. What also happens is these, and look at the scope. These are the exact same scale on the microscope. But look at how much bigger that piece of cementite is versus any of them in here. So this steel will be far more ductile than this steel. Make sense? Then you have a quenching effect. Now this is yet another microstructural change. When steel is hot, it's arranged in this type of a cube. When you quench it, you strain the cube and you trap carbon in there. So you get this kind of a rectangular shape. Really, if you look at the atomic bonds, it's more like two pyramids that are stacked point on point. So you go from this type of a microstructure to this type of a microstructure. Almost looks like a stack of needles. Now in this case, this structure is very strong compared to this one, and the carbon bands are thinner, so you don't give up quite as much ductility as you would in this type of a microstructure. So you still give it up, you just don't give up as much. Now lastly, this is what's commonly called MMFX. It stands for mixed martensite phase transformation. You have the same phenomenon on an atomic level that occurs in the quenched steel, but it's built into the molecular lattice. You see these laminar bands that are forming? The thick bands are martensite and the thin bands are austenite. They're retained austenite. Then when you tensile test the steel, the austenite will turn to martensite before it fails. So you get phenomenal strengthening from this type of a reaction. I'm trying not to be, I could be very technically correct about it, but it gets very deep, and I'm trying to shorten it and kind of oversimplify it a little bit. So I'm being careful, but fundamentally, that's what you have going on with the MMFX. So, keeping on looking here, the other issue we face with rebar is that because of the deformations, we don't have a uniform bar area. And while that seems kind of elementary in a sense, the deformations are not load-bearing. What that means is when you put the bar in a tensile machine, deformation does absolutely nothing to guarantee the tensile strength of the bar. The entire load is borne by the plug. That affects the as-tested modulus, that requires additional alloys as compared to smooth rounds, and it reduces the ductility of a piece of rebar as compared to a smooth round. You also have a phenomenon called forward slip. I'll explain it a little bit more on the next slide, but what happens when you're rolling, the steel near the roll moves forward through the mill faster than the steel in the middle. And this creates its own issues. It creates little tiny voids in the steel, especially at the bottom of the deformation. It causes uneven roll wear because of the deformations. You get a pattern called wiping at the bottom, and again, I'll explain that wiping on the next slide. And it's also the reason the industry as a whole has moved towards spiral deformations, because what the spiral deformation does is it spreads that difference in area across a longer length of the bar, so your big area is less big compared to the average and your small area is less small compared to the average. And so ironically, the very thing that's needed for the rebar to bond well with concrete is the very thing that sort of hinders its development. So here's a look at forward slip. These are two roll mill rolls, top and bottom. This is a bigger piece as it's going through the mill. And if you can imagine vertical lines right here, as they go through, you see how they get pulled forward, right? Well, when you add a deformation to the mix like we have on the bottom, you see where the bar fills it and it slightly pulls at the very bottom of the deformation. That's the phenomenon, at least in CMC we call that wiping. I'm not sure if there's really a true industry name for it, but that's what we call it. But if you look, you've got an area for the deformation, you've got an area for the plug, and you've got an area at the very base of the deformation that's smaller than all of them. So ultimately, your smallest area determines your strength. Right here, this is the thing that fundamentally determines how strong the bar is that bottom of the deformation where we have the stress riser and everything else. I know in some of the research that we've seen, the bottom of the deformation has become almost a critical point of failure. Now here's another look at it, and this is a little bit of airing some dirty laundry here. This is what happens when the base of the deformation is too sharp. The bar breaks right along the base of the deformation, but what this also illustrates, at least this compared to the bamboo bar, it's not as bad. If the bar is bamboo, it would break even sooner with even worse ductility. Now in this case, we made this change in direct response to Dr. Wasim Gadoom's research on low cycle fatigue. We realized this was a problem, so we made changes to the geometry and we got the bar to go straight across instead of following the deformation again. Now what this also highlights is nobody's been sitting still with all this research. So we've been receiving feedback from the researchers and we've been improving our bar, and it's a fortunate yet unfortunate thing that some of the data that's now being used, I would say, is the floor of the performance of the bar, because we've been able to make improvements to our bar based on feedback from the research. And I'm certainly not advocating that we repeat all the research again. All I'm saying is that the bar we're making today at grade 100 is better than the first draft bar we were making 3 and 4 years ago. Now, this is just to show that each means of strengthening the bar has its advantages and its disadvantages. Some bars are better on the tensile to yield ratio, some are not. Some have a yield plateau, some don't. Some are better on low cycle fatigue, some are better at cold tolerance. None of them in any way, shape, or form would I consider any of them to be a poor representation in any of the categories. But this is just to say they're not all identical. Taking another look at it, this is kind of your triangle of strength. You're going to have yield strength, the ratio, and the elongation. Pick the two you want and give up the one you don't want, basically. You can pick those two, and to achieve that, you get your yield strength, you get your elongation. Microalloying and quenching will generally do that. Quenching will bring the ratio down further than microalloying, but microalloying will bring the ratio down compared to conventional strengthening. Yield strength, tensile to yield ratio, add some conventional alloys. You'll gain tensile strength, you'll gain yield strength, you're going to give up elongation. You want your ratio, you want elongation, get rid of everything, temper the steel, and make it soft. So pick the two you want, you're going to give up something. Also taking a look at your grade minimums. This is something that's basically elementary, but I'm going to show it. Your spec minimum has to be above the tail of the histogram based on the way specifications are done. We have to make sure that we're well enough above. So whenever you specify a grade, you specify 100, on average you're going to get 105 to 108 based on the statistics. So now taking a look at something else, your minimum 90 KSI tensile on A615, this is actually impacting A706 because of the market demand for dual grade. Now what's happening with the dual grade is everybody wants the bar to hit both grades. We bring the strength up to make sure we hit the 90 minimum. The yield strength comes up with it. Now we're averaging 72 to 74 instead of 65 to 68. Nobody wants the overstrength, but the grades are misaligned, and that misalignment is directly causing this phenomenon. So how do you rectify this? You got equally loud voices. We need more grades. We need fewer grades. You've got an increasing difficulty achieving the specifications, and you've got the grade marking, so once you miss it, you scrap and steal. You've got increasingly divergent properties. We got to get the research done, which that's happening. And we've been making improvements based on all the research. And then the chicken and the egg scenario. So real quick, how do you get more grades and fewer grades at the same time? You redo the grades so that they line up. And that way, at least if you hit the one in the middle, you hit them all. So what that means is we would have to match A615 to A706, probably put a lower tensile to yield ratio in, no changes to elongation, but bring that tensile minimum down. And that would greatly solve a tremendous amount of issues in the marketplace and in the design side. So this is the CRSI unanimously supported draft to A706 to include grade 100. This is type W and type N. Type N's a placeholder. Grade 60 and grade 80 remain unchanged. Grade 100 added, and then these are the basic properties that we're saying we believe we can support, and this was unanimous resolution out of CRSI's Material Properties Committee. And that was a 1:17 ratio, 10% elongation. There was some producer concern about hitting 10% consistently at 14 and 18 bar, and then we're keeping the grade 80 pins. There is concern about bending anything bigger than an 11 bar. So the chicken and scenario, nobody orders it, so I'm not making it. Nobody makes it, so I'm not ordering it. Something's got to give here, right? Nobody's ordering or making it, so I'm not going to detail it. And this is a lot of what's going on. I'm glad y'all can make it at the mill. Guys, we can't bend it in the fab shops. So, but now that that's being addressed, the fabrication equipment is better. The installed base is not there yet, but it will eventually get there. And closing thoughts. Rebar is no longer a catch-all. It is honestly being treated, used, and manufactured as an engineered material. The real competition out there isn't even between us and the mills and each other and things like that. We're competing against the wood industry, who is kind of trying to take over and build apartment buildings out of wood like the one that just burned down in Charlotte. It doesn't burn at chars, but it charred to the ground. And so reinforcing concrete, it must be safe for the occupants, safe for the builders. It must be price competitive, it must be easy to do business with, and it must be adaptable. Thank you.